This video discusses simple harmonic motion. Simple harmonic motion is occurring when the position of a point oscillating about an equilibrium position at time t is modeled by either s of t equals a times cosine of omega t or s of t equals a times sine of omega t. A and omega are constants, with omega being positive. The amplitude of the motion is the absolute value of A. The period, which is the time it takes to complete one entire oscillation, is 2 pi over omega. And the frequency, which is the amount of a full oscillation that's completed in 1 unit of time, is the reciprocal of the period, omega over 2 pi. All of this is very familiar to us. Although they're using omega, this looks very familiar to just our regular cosine and sine functions. All right, we were using x usually instead of t. But you'll notice that omega is just the same as b. So when you're finding your period, yeah, it's 2 pi over omega, but to me that's nothing new because we've been doing 2 pi over b to find the period for sine and cosine before. So I always just think of omega is the same as b when I'm doing these kinds of problems. Let's look at our first application. An object is attached to a coiled spring. It's pulled down a distance of 6 units from its equilibrium position and then released. The time for one complete oscillation is 4 seconds. So we've got this coiled spring with some kind of weight on it, or object. It's been pulled down 6 units. So we're starting down here at -6. When deciding whether you want to use the sine or cosine function to write your harmonic motion, you want to think about where your object is starting. Our object has been pulled down, so it's not starting at the equilibrium position, which would be 0. And if you recall, our sine function is the one that always starts at 0. So since we're starting at anything other than 0, it has to be a cosine function. With most of these harmonic motion functions, it is a cosine function. The only time it would be sine is if your spring or pendulum was in rest position and then was struck to make it start swinging. All right, so we're going to use cosine in order, and it tells us the time for one complete oscillation is 4 seconds. Well, that's our period. So let's read our part A. We want to give an equation that models the position of the object at time t. We've already established that we're going to use a cosine function. S of t equals a cosine of omega times t. We know that a is going to be -6 because we're starting at -6. And we're going to use the information we have about the period to get our omega. Remember that the period is equal to 2 pi over omega. We know that our period is 4, that was given to us, and now we can solve for omega. I'll cross multiply and divide. We get that omega is pi over 2. So that finishes our function. Argument of pi over 2t, we get s of t equals -6 cosine of pi over 2t. In part B, we want to determine the position at t equals 1.25. All we need to do is plug that into the function we created in part A. S of 1.25. And you'll just plug this into your calculator. Make sure that you are in radian mode. And rounding to the nearest hundredth, we get 2.30. And since they didn't give us a unit of feet or centimeters, we just don't include a unit, or you can just write the word unit. And then part C, they ask us to find the frequency. Remember that the frequency is simply the reciprocal of the period, and our period was 4. So that means that the frequency is the reciprocal of that, 1/4. Let's try another one. It's a little bit different. The formula for the up and down motion of a weight on a spring is given by S of t equals a times sine of the square root of k divided by m times t. If the spring constant k is 4, what mass m must be used to produce a period of 1 second round to the nearest hundredth? Alright, so let's plug in any information that they have given to us into our function. They told us that our spring constant k is 4. And they also told us that the period is 1. Well, I can't plug the period into my function, but I can plug that k value in. S of t equals a times sine the square root of 4 divided by m. Now that t is on the outside of the radical there, so careful as you're writing it. And I'm just going to leave it like that. I'm not even going to try to simplify that radical. Alright, we're supposed to find our mass m when the period is 1 second. Let's think about how we find our period. Period is 2 pi divided by omega. We know our omega. It's the square root of 4 divided by m. And we also know that our period is equal to 1. So we're just plugging, we're going to be setting this here equal to 1 and solving for m. So 1 equals 2 pi divided by the square root of 4m. I'm going to cross multiply. Square root of 4m equals 2 pi. Next we'll square both sides. Gives us 4 divided by m equals 4 pi squared. I'm going to cross multiply again. And then lastly divide by 4 pi squared. And we get m to be equal to 1 over pi squared. Let's see if we needed to round. Yep, we want to round to the nearest hundredth. So we'll plug that into our calculator and get 0.10. Okay, one more example. This time instead of a spring, let's look at a pendulum. The bob on a simple pendulum is pulled to the left 4 inches from its equilibrium position. After release, the pendulum makes one complete back and forth cycle in 2 seconds and follows harmonic motion. Alright, so let's see what they've told us already. We've been pulled to the left 4. So that means that we're starting at -4. That gives us our A value. It also tells us that if we're going to write a function here, we're going to want to use cosine because we're not starting at 0. After release, the pendulum makes one complete back and forth cycle in 2 seconds. Well, that's the definition of period. How long it takes to do one complete oscillation or back and forth cycle. So there's our period. Okay, let's read our questions and answer them. First one, what's the period of the motion? We've already established 2 seconds. The frequency is the reciprocal of the period. So the reciprocal of 2 is 1/2. Next, they ask for the amplitude. We've established that A is equal to -4, so our amplitude is going to be the absolute value of -4, which is +4. And now we want to write a function that models the displacement d of the bob as a function of the time t after release. We'll assume that the A displacement to the right of the equilibrium is position is positive. So since we were pulled to the left, we're starting at a negative. Oh, S of t. We've already stated that A is equal to -4. -4. We're using cosine because we're not starting at 0. And then we'll have our omega t, and we need to figure out what omega is again using the period. The period is equal to 2, and we also know that the period is equal to 2 pi over omega, so we're just setting these two equal to each other. 2 pi over omega equals 2, cross multiplying. 2 pi equals 2 omega. Dividing, we get omega to be pi. That completes the argument of our function. S of t equals -4 cosine of pi, not omega, pi times t. Lastly, we want to find the position and direction of movement of the bob at t equals 1.25 seconds, and we'll round to the nearest hundredth. We're plugging in, finding S of 1.25. It's -4 cosine of pi times 1.25. And you'll want to plug this into your calculator. Make sure you're in radian mode, and we'll round to the nearest hundredth. We get 2.83. And they did give us a unit of inches. But now we need to determine the direction of the movement. Is it swinging to the left or is it swinging to the right? So let's think about how we would figure that out. We know that the entire period is 2 seconds. So it takes 1 second to go halfway, and then another second to swing back the other way. And the position that we just found was at 1.25 seconds. So it's already swung all the way to the right, and now it's beginning its backswing. So we're at 2.83 inches, and we're swinging to the left.